Good day, sir. My name is Katal Tsubani, and today I'll be taking you through a summary of the project that you had given to me, where I had to design a water supply distribution network for the Tshipiso local municipality. In this project, I was appointed as an engineering technologist to do an analysis of a water supply system that is going to be implemented by the Tshipiso local municipality. Tshipiso is a town in Limpopo under the jurisdiction of the Vembe district municipality. This project is intended to provide water supply to the 4 townships of this town in accordance with the municipality's water services development plan. This town in total has an area of 1.5 kilometers squared and houses an average population of 2,000 people. On my right-hand side is just a drawing of a map that we were given on the project brief for the project. In order for me to undertake this project, first I did my case study, and the first thing that I asked was, what is a water supply distribution network? A water supply distribution network is a network that is comprised of several components like pumps, pipes, reservoirs that work together to transport water from one or more resources to multiple demand centers. It is very vital that the water that is supplied in sufficient quantities and with sufficient pressure. Next slide, please. There are several network components that make up a full, complete water distribution supply network. These are our water source. This is where we'll get the water from the entire system. For the entire system, this can either be rain or a dam or a well, or in our instance, it is a river, Nyangwe River. The second component is water treatment plant. Here, water is treated to ensure that it is clean for consumption. Then we have a storage tank that is required for the continuous supply of water systems whilst pumps are not operational. This means that when pumps are switched off, you need to be able to still provide water to the townships. And then we have our pumps. These are used to transfer water and help move water from one point to another, either from the river to the treatment plant or from the treatment plant to the bulk storage tank. And then we have our pipes, which are used to move and transport water through the network to various locations. There are several pipes that can be used in this water network, like ductile iron pipes, galvanized steel pipes, and PVC pipes, and many more. I just showed an example of 3, and in this project, I decided to use PVC pipes, mainly because as compared to steel pipes, these are less prone to rusting. And rusting, if it occurs in pipes, can contaminate water, thus compromising the health of consumers. Next slide, please. There are 3 types of water distribution systems. We have a gravity-fed distribution. This system is applicable when the level of water storage is higher than that of the area that is being supplied with the water. This means that it is applicable when our storage tank is on a hill or it has been raised, perhaps on steel clamps at a higher elevated volume. And then we have a pumping system. In this system, water is supplied by means of continuous pumping. We have a dual system. This is a distribution system where both gravity and pumping are used. As is the case in my project, the system that was applicable was a dual system because from the river to the bulk storage, the elevation is raised, meaning that our bulk storage is at a hill. Therefore, we need pumps to get the water to the hill. And from the hill, which is the storage tank, to the demand centers, the elevations are lower, meaning that our system is gravity-fed. Next slide, please. In order for me to be able to execute and do my design, I used the EPANET software. This is a software that is a computer program and is used to perform extended period simulations for hydraulic and water quality behaviors within pressurized pipe networks. A network consists of pipes, pumps, valves, nodes, and reservoirs, as I've already explained them in the above slides. This software also tracks the flow of water in each pipe, the pressure at each node, the height of water in each tank, and the concentration of a chemical species throughout the network during a simulation period. Before I did my design, there was some data that was stipulated in the project. For instance, I was given my demand for all the 4 townships. The average demand for the first township was 60 liters per second. The second daily demand was 75 liters per second. The third was 85 LPS, and the fourth was 135 LPS. And it was stated in the project that for me, I needed to first initiate that. I needed to first assume that the initial diameter for all the pipes is 300 when doing the design. And then I had to calculate my elevation for all the nodes that were going to form part of our system. From the project, it was stated that the Nyangwe River will be used as our benchmark. Therefore, meaning it will be our 0 mark, and we'll have to reference the Nyangwe River for all the nodes that are going to be needed, from the pumps to the water tanks, from the water tanks to the demand centers. And in me doing my calculations, I found the following elevations. From the river to the water treatment plant, the elevation is 17 meters. From the river to the bulk storage, the elevation is 74 meters. From the river to junction 1, 47 meters. The river to junction 2, 40, and so forth and so on, until I got to my last elevation, which was river to demand center 4, where I found the elevation to be 30 meters high. Now that I had my data, I could carry on and do my design. The first step of the design, after having opened the software itself, is setting up the defaults. With defaults, I had to set up the notations of whether or not I went to the software to show all the nodes, or I must just show the links, and also set up link IDs. Should they all increment at 1, or should it just be from the first node to the last node? They must just increment in ascending order. And then after that, it was stated in the project that I had to set up my defaults for the units that we're using for the formula. It was Haitian Williams, and then also set my units to liters per second. And just to explain further, the formula that we use, which is Haitian Williams, is a formula that is used to relate the flow of water to pipes, properties such as pipe roughness. And the formula for this equation is U is equal to K multiplied by C multiplied by R to the power of 0.63 by S to the power of 0.54. After that, I had to set up other data components like my times, where I was given multipliers, a time pattern of 1.4, 1.4, 0.6. And this time pattern had to be applied to all hours of my 24 hours, because it was said that the time pattern will apply for 24 hours. So as I already mentioned, sorry, the time pattern is actually 0.6, 1.4, 0.6, 1.4, 1.4, then it repeats itself again, 0.6, so forth and so on. And also I had to set up the duration of the entire distribution system to be 74 hours with a time step of 4 hours. After that, I continued again to move on and set up my pump curves, where with the volume of the pump curve being 600 liters per second, and also setting the head to be 80 meters. It was also stipulated that I must ensure that my velocity does not exceed 1.5 meters per second. And also calculate the required storage tank for our storage reservoir. And after having calculated that, I found that the storage that we have is greater than the required storage. So therefore, we'll have sufficient water stored in the bulk storage reservoir. After having set up all my nodes and my links and the relevant data into the software, I ran the initial run, and the run was unsuccessful. And the status report from the software was that this is due to negative pressure. And to get rid of this, I had to increase my pipe diameters. And on the initial run, since I mentioned that there's negative pressure, this means that the flow of the fluid was too compressed, thus it was not flowing as it's supposed to. So in the second run, after having increased my pipe diameters, the run was successful. And these were the pipe diameters that I ended up with, which were pipe 1.1, 1,101 millimeters, all the way to 450 millimeters. And when I ran my simulation, it was successful, meaning that there is no negative return, there's no negative pressure. And as seen in this table below, the velocity for all the pipes is less than 1.5 meters per second. This is all, and thank you, sir.